Good evening, everyone. I welcome you all for today's webinar on data structures and algorithms organized by the IEEE Computer Society of University of Peradeniya branch. We're thrilled to have you all here today, whether you're a participant in IEEEXtreme or someone just interested in learning more about today's topic. The session today is designed for everyone, so regardless of your background or level of experience, we hope you will find it engaging and informative. I would also like to remind that if you have any questions, please use the chat box or unmute yourself and speak. Before we dive into the session, I would like to take a moment to introduce our esteemed speaker, Mr. Supul Editisinghe. Mr. Editisinghe is a passionate advocate for STEM education and serves as a volunteer and community manager at STEM Up. In addition to his work with STEM Up, he is a final year undergraduate in his computer science honors degree at the University of Peradeniya under the Department of Statistics and Computer Science. We are honored to have you here today, Mr. Supul, and the stage is yours for sharing your wonderful insights and experiences.
Am I audible?
Yes, you're audible.
Okay. Okay. Thank you for the introduction. And also welcome everybody. Supul Editisinghe. Okay. So today we'll be talking about the structures and the importance of algorithms and issues. Right. Just okay, so yeah, I will be conducting the session in English, but yeah, so if anyone have any questions, please feel free to ask this lecture. This is a workshop panel session. So all right, right, let's dive into what is data structures and algorithms, especially in regards to the IEEE competition. So we will be looking into mostly what are graphs, graph algorithms, which are a really special type of like solving problems, and also sorting algorithms and some hashing algorithms and what. Okay, so okay, so probably most of you guys are in the computer science, computer engineering, or in a programming related area. But even if you're not, I think you will be able to follow me on this session. All right, but yeah. So also I should remind you that this session is not regarding to any specific programming language. So you guys can follow and practice, and almost most of the time you can basically do this on any language that you're comfortable in. Okay. All right. So I'll be using this abbreviation DSA throughout this session. DSA stands for Data Structures and Algorithm, which is a common name in computer science. Okay. So why do we need data structures? Because we all know that we have variables, no? We have integers, we have tuples, floats, strings, and so on. So here we will be talking about things like queries and queues, stacks, and also matrices, tables, and whatnot. Why do we need those things, and how are we using these to solve problems very effectively? Okay, so basically, the DSA actually stand for two things. First thing is data structures, and the second part is algorithms. So data structures, they basically helps us organize and store data very effectively. It's like sort of like we are us studying for an exam. Right? Some of us, let's say, we have a we have this periodic table, right, in chemistry. So we, some of us can actually remember the entire table from memory, but some of us use some mnemonics. No, we will be putting that into a some sort of a song, a phrase, something. Or otherwise, some of us might have done some mind maps. So we will draw a map and we will draw arrows and like uh, in like the main idea is we were trying to remember and retrieve those information very effectively. So that's the same situation in computers as well. So yeah, data structures do just that. Okay, algorithms, that's like how to solve a problem. So basically programming challenges, IEEE extreme, or in any case, what we call programming is basically solving problems. That might be designing a website, maybe we are designing a inventory management system, whatever. So basically, we are solving a problem. So in this case, that's not different. So algorithm is a step-by-step instruction. How are we going to solve this problem? Okay. So what we are going to do is optimize how to do this. So we will be talking about these things like how to optimize like a certain algorithm so that it would run faster. So also, let's say we are making tea, right? So when we are making tea, we know that we have to follow a specific set of steps. Like we have to boil the water, we have to get a cup and maybe some tea leaves in it or tea bag in it, and then for the boiling water, we just can't mix up those steps. No? We can't just let's say uh, put the water on the cup, then the tea bags, and then boil it. We can't do that. We have to do that step by step. And also, let's say the boiling, we have it will take 10 minutes to boil the water. And also, we need the kettle. Right? So basically, we need a specific amount of time to make tea. So there's this, maybe you guys have heard. So it's like, let's say, one person can do this task in uh, 10 weeks, and if 10 people get together, maybe they can do it in 1 week. But uh, let's say uh, we are talking about giving birth to a child. Okay, so one woman may give a, like from the pregnancy to the delivery, it would take 10 months, right? But we can't just speed up the process by like involving 10 minutes. That is not going to happen. So like that, in algorithms, there are certain cases where we need a specific amount of time, and there are certain cases where we can speed up the things. Right? That's what we mean by time complexity, and the space complexity is basically how much space we need. In the case of computer science, we are talking about our RAM, our memory, our the hard disk, whatever the memory we are using. Okay, right. So these are like the most common data structures. I hope you guys have an idea that you may have seen these things. Um, Arrays, basically a fixed, like it's a set of like numbers, names or something. That's like it's a continuous set of data. So yeah, the main thing is array is fixed size. So we are introducing this concept called linked list, which is a dynamically changeable. Like if we say this is an array of 10 elements, we can only have 10 elements in it. If we have 11 elements, we can't fit it into the array. Let's say we have a house with 10 rooms, and we are putting one person, so we can only put 10 people. So linked list is like it's an array. So it's sort of an array, but it can change the size of it. So if we have 11 elements, they can fit 11 elements, and if we want to add one more, they can do that. Okay, like that. So also there are these stacks and queues, trees and props, and hash maps. We just let's talk about these things when we are using them in practice. I think that could be a very efficient way rather than me doing what are these data structures and so on. Yeah. Uh, all right. So these are just some illustrations of those things like linked list, analyst, and hashing. Okay. So algorithms, how to solve this problem. So we have some classifications of algorithms depending how we are approaching the. Okay. So main basic thing is like let's say we have a. Okay. Okay. Let's say we have this set of numbers of something, and we have to search whether a specific, let's say that this is the X element, and there may be some data in those slots. Okay, we have to search for X. So how are we going to do this? The easiest way is go one by one. No? Yeah, that's it. That is an algorithm. Definitely, that is an algorithm. But the thing is, that might not be the most effective way. If there are like 100 elements in the array, it would take a long time to reach this point. No, because it's at the far end of the array. So there are some very, let's say, clever methods to achieve that result much quicker and in a different way. So these things are mainly like that: greedy, divide and conquer, dynamic programming, and backtracking. Okay, so mainly we will be talking about some classic algorithms and greedy algorithms, but also I will walk you through with some things that depends. Okay, uh, yes. So let's say you would log into HackerRank or LeetCode or something, and you would see, yeah, here's the problem statement. Okay, we have an array. We need to find the largest element. Okay, something like that. So how are we going to approach that? Right. First thing, take a deep breath and read the question carefully, just like any other uh, paper or something. Yeah, read the question carefully, and then just identify what is happening in the process of solving it. Okay, so let's say we are solving a problem where we have to find the largest element. Okay, we have a list or an array of elements, and we have certain numbers, different numbers, and we have to find the largest one. Okay, so how are we going to find it? That's the first. No? So we have to think, what are we going to do? Afterwards, we can think, okay, so the numbers are basically sorted. So maybe we can use that. Okay, so if numbers are sorted, definitely the largest number could be either here or here, something like that. If the numbers are all jumbled, that is not possible. No, if one is here, three is here, and two is here, four is here, yeah, we can't do that uh, thing. Yeah, we can basically find the largest number by looking at either of the ends. No, we just have to go one by one. and see that we can find it. Okay. So depending on the question, we can decide how the data structures and what is the approach we are going to use. Okay. So also, yeah, I will be talking about these time complexities because, yeah, uh, just to have an idea, can you guys just do a show of hands if you guys have attempted some sort of competitive programming, like in HackerRank, maybe a hackathon, uh, something. Just raise your hand if you have. If not, that's also completely fine. I'm just trying to get an idea. This one. Uh, there are a couple of people, and I hope rest also might be have tried like solving some problems at HackerRank, maybe at the university, something. Okay. This whole thing is basically how much time we are going to use, and in yeah, in also we will be looking at how we would be managing that time. Okay, so yeah, the easiest one is sorting. So let's start with how to sort things. Yeah, if you guys have any questions, I think it would be better if you can ask then and there, so we can clarify it and move on. Yeah, okay, so I will do sorting because I think that is the most easiest and straightforward things in work. Okay. So before that, before working on like the sorting algorithms and discussing those things, yeah, I would like to show you guys a couple of uh, resources that you can use, and I would like to show you some of the questions that you might be receiving if you guys are creating on the extreme of some other okay. So basically this is lead code, and you might have seen this definitely. HackerRank. Yeah. Yeah, this is a very famous website where there are certain questions where we can, yeah, you can try it out, and yeah, like that. Basically you can use any language in most of the hackathons, I believe. If you are familiar with C, that's great. You can go with it. But if you are like a Python fan, yeah, you have that option too. Or C++, Ruby, PHP, whatever. Okay. Just you just have to know one programming language, and the platform probably has that compiler, so you can just write the code and run it, and then you can check whether that's the right thing. So we have the proper statement, and how the things are like. Uh, like these are the inputs that we are getting. So we have to do a certain calculations, and we have to output something. Okay. Yeah. So basically, that's what's happening. And also, like, I just wanted you to, if you haven't already, just browse it. HackerRank is a really good place for mainly, I would say, beginner players. I would say players because this is a competition. Okay. Okay. And also, if you are comfortable with certain, because uh, HackerRank doesn't have those time constraints and uh, how fast you are doing the competition. I don't mean how fast by how fast you are typing, how fast the program executes. Yeah, the HackerRank doesn't generally look into that really rapidly. So yeah, this is a very good place to start on. I think. Okay. So yeah, for advanced players, I think you probably have seen those things. This is and there's this lit. Okay. These two have some of the like really advanced and complex questions I have seen. So yeah, this is the legacy things. Yeah, if you are if you want like get some hard questions, I think workforce might be the best way, but it's a bit all. Yeah. As you can see, it doesn't even have a really good anything. Okay, let's go on those algorithms. Right. And in the meantime, if you don't have any language installed in your computer, LeetCode and other almost all the platforms has a playground, so you can just type some code on it. So you will see how much time it took to like run the code. So here it says 20 seconds, and you get the output. And also, yeah, you can do then you can do like anything. Right. So it's more okay. Sorting algorithms. Okay, so sorting means we are just we all know what sorting is, okay, right? Yeah, basically we will have a list of numbers or letters or something. Let's work with numbers because I think that would be easier. But definitely you can think about this maybe like we have A, C, and so on, like letters. So we can sort them alphabetically. Or anything. Sorting is just arranging them in some order. Okay, let's say we have some numbers. Uh, so how like what would be the best strategy for us to like pardon my bad handwritings? This is 3. Okay, so what would be the best method to solve this? Okay, so before we can consider what is the best method, we have to know what is the situation, what are the things that are possible. No, what are the like methods that we can use to solve this? The easiest way is we can just go through this and see if there is any like everything is in order. Like in this case, 3, 4, 5, 6, 9. Yeah, they are in order. They're in the ascending, right? If they are not, we have to change the order in some way, right? Okay. Yeah, that's basically what a sorting algorithm does. So there are two main types of algorithms. First one is called comparison based, and the second one is non-comparison based. Yeah, this one is kind of a clever way to do this. So basically, let's say we have 3, 1, 2, and 0. Okay, so this is not sorted at all. Okay, so we can like compare two numbers. Okay, let's take this one and this one and see which one is the largest and which one is the smallest. We can see this is the smallest one and number 3 is the largest. So maybe we can swap this. Okay, we can put 1 here and 3 here. We can just swap it and say is here, 3 is here. So these two are sorted. So we can do that thing like compare two elements and sort it. So that is what we mean by comparison based. And the second one is we are not comparing two things. We are just uh, like doing something else. So the array itself will be sorted. Okay. Right. The easiest one in the book is bubbles. So that just it is really simple algorithm, and it is just going to take two elements and swap it, compare it, swap it. Okay, that's all there is to the bubble sort. Okay, let's see. So we have this array. So we have 77, 35, and so on. So we will like take an edge, okay, either from here, from here. We will take two elements that are adjacent. Okay, 77 and 42 are the adjacent. Like we can say first two adjacent elements. We will take both of these, and let's say in this case we are doing sorting in the ascending order. That means the smallest element will be in the very beginning, and the largest element will be at the very end. Okay. So how this is going to happen? Take two elements and compare whether this is smaller than this, because we need the smallest one at the leftmost slot. No? Okay, 77 and 40. We take it. We compare it. Yeah, whether is it small? Yeah, that's not clear the case. No, in this case, yeah, 42 is smaller than 77. So we will swap those two points. And we can see here 42 has come here and 77 is the second step. Right. Now we have sorted this out. Now we will be taking this two and do the same thing. So we can see 35 has come here and 77 is pushed further. And we can do the same thing over and over until we reach the end of the array. Right? At the end, we will be having like, let's take these two. 12 will be here. Okay, 42, 35, 12, and 77 will be here. And these two will compare. And yeah, actually 77 is the smallest one, so he will stay here. And there's the 1 and 5. Definitely he is the smallest one. So 5 comes here, 101 goes to the rightmost edge. Okay, now yeah, this at the first glance doesn't make any sense, right? Yeah, this is not sorted out at all. But if you would compare the starting array, which is basically this, and our final result, we can see that the largest element has somehow come to the very end, very right end. Right? This is what we do by bubble soup. So we can do again and again the same thing until the array is sorted. Yeah. So yeah, here's the result from each iteration. So we can see 101 has been here. So this is the rest of the array. So if you do the same thing again, the 77, which is the next largest element, it would come here. Then 42 would come here, 35, 12, and lastly, I will stay at the same place. And the array is sorted. Yeah, this is the bubble sort, and it's like it's crazy simple, right? Okay. Yeah. Now let's do some other sorting algorithms. Yeah. Now the thing about bubble sort is it's crazy simple, but as you can see, how many steps do we have to take so that the entire array is sorted? That's like it's really expensive, right? Expensive by means the amount of computation you have. That means let's say we have 6 elements here, and at the very first iteration we have to do comparison 6 times. No, then do it again 6 times, again and again. So like we have to do 5 times the whole thing all over. There we have 6 elements. Suppose like it's like 30 steps, no, to sort the entire array. So suppose we have a list of 100 elements. What is it going to be like? N is 100. So as we can say that there are n minus 1 steps to sort the entire array, at most, right? So n minus 1 would be 99. So 99 times 100, yeah, that's a lot of steps to like sort an array. And also, right. So because of that, we have some other ways of sorting. So one thing is called merge sort. So hope you guys can see. Yeah. Merge sort. So yeah, it's like so here we will be like, here we are talking about this divide and conquer paradigm, which is nothing really huge, but okay, let's talk about this. Okay, so just to suppose we have a huge array, like let's say this is the array 7 4 8 9 blah 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 blah. Okay, let's completely forget the this bottom part, and let's consider our problem at hand. Okay, what is our problem? We have to sort an array. Right? The array is 7 4 8 9 5 3 5 6 2. Those are the numbers we have to sort. Okay, so what they would be like, we would be doing is we would let me read this. So let's go to some this we can sketch. Okay, so we have our number. So this is an array, right? These are separate slots. Or we can let's go with slots. Okay, so suppose this is we have 100 elements. That could be the case, maybe 1,000, maybe 100,000, whatever it is. Okay, so like doing the bubble sort is going to be crazy, right? And crazy that makes sense. So what we are going to do is divide the array into two halves. Okay, so we have this half, the left portion and the right. So let's say left part is 7 4 8 and 9. Okay, so we have 3 5 6 and 2, and we divide it again. We have 7 and 4. We do the same thing again. Okay, so we have like, we are just breaking those in smaller parts, so we can sort it easier. So we can sort two numbers very easily than 8 numbers altogether. No? So idea is, we would be like, the idea of breaking it to like single ones rather than twos is like, it's just easier for us to, I mean, and also it's the name of the sort is merge sort, right? Merging means we would break it into smaller pieces, then we would append these like pieces in a way that everyone is getting the uh, everyone is getting the smallest one at the very left edge. Okay, so so we have dropped the array into singles, right? We have 7 and 4. We have divided the array into smaller pieces. That's the first thing, right? We said divided. So what we are going to do now is piece these things together in a way that they are in the ascending order. How are we going to do that? We would piece this one right in front of 7. No, we would piece this 3, 4, and so. Okay, we took this one, put it forward front, this one, and put it in the back. Right. Then we do the same thing here, each and every element. So what are we going to be end up with? We are going to end up with 8, 9 here, right? 3 and 5 here. So 3 and 5 here, and 6 becomes 2 and 6, right? So each of these small subtrays are sorted. No? So we are going to do the same thing again. We are going to merge these two together in a way that the same order applies. Right? We have 4 and 7, we have 8 and 9. So we would just look at the arrays and we know first element is going to be the smallest. So in the next array also, first one is the smallest one. Okay. Now that we have that knowledge, okay, let's come here. So right, I think now you know what happened here, right? Is divided into smaller subarrays so that there are single elements all over. Okay, so we are going to merge it. This is the dividing part. This is the merging part. So in the merging, we would order them up in a way. In each step, the elements are ordered in the ascending order, right? So we know when we are merging these two things, I think can see. Okay, suppose we are merging these two parts, we have to merge it into one array, right? So we are going to look at the very first two elements because it is like since these smaller parts are sorted, it is definitely going to be the smallest one in either of these. So we would compare these two and we can see what is the smallest. So let's put 4 here and we would just ignore this and let's select this. So this first element in here is now 7 in subarray. So we would compare those two and it's again 7. So we would bring it here. Then we have this. So bring the first element here and we are left with 9. So 9 comes here. So we have 4 elements that are very easily sorted. Same thing goes here. Okay, 3, 5, 2, 6. So we would compare. Second 2 is the smallest one, take it here. 3 is the next smallest one, take it here. 5, then 6. So now we have two subarrays. We just have to do the same thing once again, right? Just compare the very first elements and put it in the array. Okay. Yeah, this sounds like a lot, but did you guys notice I was doing same steps, like same things over and over? What was that? First, I would divide the entire array, right, into 2. Let's take the array, divide it by 2, and then take each of those subarrays, divide it by 2 until one element remains. Okay, so afterwards, I would just take 2 parts and merge them so that like compare the first both elements and take the smallest one, put it in front, and the next smallest one then, and like this. Okay, so do the same thing to here, right? Compare first like topmost elements, find 8. Yeah, 4 is the smallest. Take it here, right? And again in this step also Yeah, compared to elements, take the smallest one in front. Yeah. So like I will be sharing the slides. So this is like how we can do this merge sort in Python. Okay. Uh, So what would happen in this case? So we know that the whole thing is basically taking very few steps, unlike bubbles. No? We just had to sometimes if we have 8 elements, bubble sort had to we had to do 56 steps, right? Uh, yeah, sometimes it is 56, right? Yeah, 56 steps, and here we don't have 56 steps here. Okay, so I hope you guys got it. I think yeah. So let's move on to the next one. This is like very like okay. So you guys notice that in the bubble sort it's really easy to understand. Then when it comes to the merge sort, we really didn't understand why was it uh, faster. Maybe you guys did. Maybe you guys didn't. I didn't at the first time. Okay. So yeah. So basically Um, that was like, yeah, that's weird. But when we look into like how the same thing repeats again and again, yeah, that's a loop, right? Yeah, we are taking uh, some set of instructions and repeating it. So yeah, and that way it kind of worked faster than a bubble sort. So this is crazy fast for computers. Okay, so that's why it's called quick sort. But it takes a minute to for us to get into the mindset of that idea, okay, because it's kind of a crazy idea. Okay, so let's just ignore the descriptions and let's just look at the arrays and let's uh, yeah, I'll walk you through this. Right, quick sort, that is also using that breaking the array into two parts idea. Okay, but they are not doing the breaking into two parts in the like taking the size of the array and dividing it to they instead they are like taking a pivot. Okay, a pivot like you guys know what a pivot means in physics, right? Let's say this is a like this is a board and like we can balance two like weights in here, and here we'll have a pivot. No, this is a pivoting point where it stays and we can balance it, right? If we have a larger weight here, we can move the pivoting point like uh, very close and it would get balanced. Okay, yeah, so with uh, extra information, but yeah, that's the idea. We take a single element and we call it pivot. Okay, in this case, let's say 4. 4 is the pivoting element. Yeah, that can be anything. So let's say we'll take, okay, so we would scan the entire array and see if some element is larger than 4. So if some element is smaller than, that's the entire thing. Okay, so let's look. Okay, 4, and let's take the first element. Is it larger than 4? So it can stay here. If the element is larger than 4, then it would come uh, after the uh, how that is going to happen is it's like this. So the first step, we would read the 2 and see. Yeah, that's smaller than 4. So let me take the second element, whether it's smaller than, it's not. Okay, so here it might not be very visible. Yeah, we would be dividing like those 2 into 2 places. So 2 stays here, it stays here. Oh no, okay. Take, so is it smaller than 4? No. Okay, so it belongs to the second group. So we can see the lighter color one is the first group, the dark color one is the second. How are we going to divide that? It's just yeah, that belongs to the second group. Okay, so let's take the next one. Yeah, 1. Okay. Is it smaller than? Yes, so it belongs to the first. So first group is here, second group is here. So what they are going to do is push it right in between those 2 lists. So one is moved next to 4. So first group stays here, second stays here, right? Yeah. Yeah, don't worry about this these 2 elements swapping. Yeah, that's a mistake. Right, let's take 3. Yeah, is 3 smaller than 4? Yes, so it belongs to the first group. So it's moved to here, right? As you can see, 5. Yeah, it's larger, so it can stay in the second. 6. Yeah, larger. So the second. So at the end, the pivoting point is not to the middle of the 2 groups. Okay, yeah, that's just the idea, right? Why did we do all this? Yeah, debug. Yeah, the idea was take a pivoting point, break the entire into 2, then do the same thing again and again. It's like merge sort in a way. It's not like merge sort in a way. In the other way, okay. So basically, what happens is take the pivot, break the array into 2 parts. Okay. So we have here the pivot was 24. So we can see 24 was the pivot. So every element that is smaller than 24 goes to the left side. It's larger than 24 goes to the right side. Yeah, 24 is here, and these guys are smaller than 24. These guys are larger than 24, and that was done. So we take the we take those 2 sub-arrays. Okay, take it, take a pivoting point, do the same thing again until there is 1 element left. Okay, yeah. Like as you can see, okay, we take the pivot point, break it into parts according to the limits. Okay, so we have 2 and 3. Then here the 3 was taken as the pivoting point. So there's no element that is larger than 3. So both of those elements belong in the same array. So they keep dividing and dividing it into singles. Like here we can see 4 stayed here, 3 stayed here, 8 stayed here, 6 stayed here, and 5, 7, and 2. All right. Here, this is the interesting part. Okay, 4 was at the very middle. Yeah, that's okay. So 3 stayed at the second index, right? We know how array is indexed, right? 0 to, it starts with 0, 1, 2, 3, 4, 5, 6, and 7, right? So the 3 stays at the second uh, index, right? And the one was taken as the pivot. It stayed at the 0, like the first index. Second goes to the first index, likewise. Once the whole this thing is done, what happens is the array would sort it like I put those indexes, indices for a reason. Okay, so as you can see, one has the 0th index, two has the first index, 3, 2, and 4 has the third index. And it's the same for this. Okay, so these are not different arrays. Okay, it's like it's a programming trick where we just take these three parts as an array. Okay, we know how to do it. Right. Once this breakdown is done, the original array itself is worded like this. Yeah, it's like a magic. It's like some kind of a sorcery, but that's what it happens. So that's why it's called a, yeah, it's a kind of mind boggling. But yeah, that's the fix. Idea is take a pivot, divide it. Take a pivot, divide it. Take a pivot, divide it. Once you are done with dividing, the array should be sorted. All right. So that's about the quick sort. So I would like to just another one example, like a different method of sorting, so you guys have a comprehensive idea on what are the different methods that we have for sorting. Okay, so if I would ask what was the, like, let's say, what happened in all the previous sorts, they were comparison based, right? They would compare two elements, do something, swap something, and we would have the final result. Right. Here, this one is a bit different. It's called radical sort. It's one of the kind of like, yeah, we'll see what happens. Okay. Suppose we have large set. Sorry. Right. Hope you guys can see those columns, like, or columns of numbers. Right. We have a large, in this case, we need to have a large number. Okay. So suppose we have like hundreds numbers in the range of hundreds. If we were going to sort each, suppose we have 100 numbers. Okay. If we were going to compare each and every number, that is a whole, like, it's crazy, right? So when we are presented with something like this, or there are your phone numbers, right? Something like that. When that's the situation, a small trick that we might have used in our, like, in Predator line, maybe when we have a set of those numbers, we can sort each and every decimal place separately. Okay, if you would start with the very least significant value, which is the decimal case, the ones, yes, and then we would sort the next one and the next one. The ending result would be a nicely sorted array. Yeah. So what we are going to do, take the significant limit, which is the number one's place, and sort it. So here in the second column, we can see the least significant element is sorted. So 9s are here, 7s are here, 6, 5. So yeah, smallest one here, largest one here, and it's in the ascending order. Do the same thing to next significant value. Then to the next one. Right? We have sorted this one, 4, 2, 2, 3, 3, 4, 5, 5. So when we are doing that, the entire number shifts, okay? Not just the number, right? We have 329. It is gone to this place. Then 329 has come here. Okay. Likewise, once the whole 4 columns were done comparing and sorting, this is the final result. And in that result, we can see 329 is the smallest one and 839 is the largest one. How did that happen? Yeah, that's a really neat trick in number theory. Okay, so yeah, the Python code is a bit tricky. Right. So I think yeah, that kind of covers different ways of sorting. Okay. Do you guys have any questions regarding sorting by any chance? Yeah, feel free to ask. All right. So let's just talk about different strategies. So yeah, one thing I am supposed to you guys is greedy algorithms. So before I get into the greedy algorithms, I just wanted to like give you guys what is a greedy algorithm and why it's called greedy and other methods of doing that. Okay, so basically it's a way of conception and how we are going to break the problem into smaller parts. Okay, so when I yes, yes, definitely we are free to choose any pivot point, but that slide. Right. You can see right. Okay. Here uh, on the very topmost step, we can see they have chosen 4. Okay. Yes. The pivot point is in most cases random. Otherwise, they would be using the last element of the array. This and here also is the case for the last element was 3, 1, then 2. In the right side also, that's the same thing, right? 8, then 6, likewise. So yeah, you can like here's the thing. Algorithms are just steps, okay? So if your specific problem demands really creative way, like you might notice that yeah, like mainly my idea was the pivot as like suppose the pivot point is like in the very median range or mean range. Like mean range, what I mean is the very middle. Uh, Definitely the array is going to be split into very even 2 pieces. The advantage of that happening is when the array is divided into very equal pieces, the number of steps you have to uh, do into do until the whole thing decomposes into single elements becomes very small, right? Now we can see the thing here. Here we have an array of 3 elements. Since 3 is like the very like it's a edge number, you would it would take 3 steps to uh, break this into singles. But in here also it's a 3 element subarray, right? But the number that was chosen here, the 6, is in the middle. So it would take just 2 steps, like this is the first step and second step. Here it would take 3 steps. Or you can say this is 2 steps and this is 1 step. So yeah, when the array is divided very equally, the number of steps that we need like drastically was done. But yes, your point is valid. Yeah, we can choose any pivot point, but thing you have to remember is choose it in a way that it reflects your problem, right? If that's sorting some numbers and it's not really time consuming, maybe you can take the rightmost one, maybe leftmost one. Yeah, that's going to be a judgment call, I think. Okay, so we did talk about divide and conquer paradigm, which basically breaks the problem into smaller pieces, which we saw in merge sort, right? We would break the array was the problem into very small pieces, basically into single elements. Then conquer. Conquer means process those smaller pieces, smaller subproblems separately. Then aggregate those things, and we have like combine the solutions, and you have the answer for very complex problem in a very fast and easy way. Okay, so then there is this idea called greedy search and like greedy algorithms, which was I think you can see right here. Yeah, greedy algorithms. So these are like brute force is like going one by one, divide and conquer. I talked dynamic programming, that's a bit advanced concept where we would break it into smaller pieces, compute it, and remember it. Here we don't have that, we just merge it. Okay. In dynamic programming, we would just remember it and like remember it on a table or something. Then when like it's like this, suppose we have to find uh, the factorial. You guys know factorial, right? Factorial of 3, and we might have to find some factorial 5 in the in a different place. Okay, sorry guys, I just realized the screen is okay. Let's fix now. Right now the idea is basically we know factorial, right? 1 times 2 times 3 is the factorial of 3, and 1 times 2 times 3 times 4 times 5, that's the factorial of 5. So if we have to calculate factorials from 1 to 10, the thing is we are going to let's say 2, 3, 5. This part we have already calculated, right? So if we have like saved this in some sort of a data structure, then we might be able to like retrieve it and plug it here rather than calculating the entire thing again. And we just have to calculate these two parts, right? It's like that. It's what we call dynamic programming. And yeah, let's move on to greedy algorithms. That is really interesting parts. Okay, and also kind of a quite relevant idea, right? Greedy. That means basically we would just look at our situation and try to make the best we can. Okay, so take the current situation, try to make the best decision that has. Do the same thing again and again. Like so, we can call that the locally optimal choice. You can give it a name. Uh, we would just take our situation, get to the best thing that we can do at that situation and move on to the next step. So by doing that, we would assume it would result in the most efficient or the optimal solution for the entire problem, right? It's like that. So one of the very famous problems in 3D problems is knapsack problem. Okay, so it's like knapsack is kind of a, let's say we have a backpack and we have all those sizes and like this guy is trying to steal something, let's say, just a figure of speech. Okay, the stealing is bad. Right. We are trying to, we have a bag which can fit 15 kilograms of uh, goods or something. Okay. So we have some yeah, which are different in sizes, like in weights, and also they were different amounts. So we can see the 12 kilogram block only worth 4 plus. Here, the 4 kilogram block is worth 10 plus, like that. So how are we going to uh, fit the most number of like elements in this backpack so that this guy would leave with the most profit or the most valuables, right? That's what the knapsack problem basically means, right? So how we are going to do that? So there is this, there are yes, yes, yeah, it's a really good question. I will definitely answer this in a bit. Yes, this involves idea of dynamic programming. Yes, yes. Please give me a second. I will answer that. Right. We will. Yeah, knapsack problem. Right. So how are we going to fit the most amount so that we would leave with uh, the most valuables, right? So there are two types of knapsack problem. So one is 0-1 knapsack. That means either you take a part piece or you don't. Okay, it's like suppose we have like boxes of things, so we can't just break one down and take apart. So the other one is fractional knapsack. The fractional one basically, let's say we have some sort of like marbles or sand or cement or something where we can take a certain portion and take it away. Here we can't do that. So this is a 0-1 knapsack. So how are we going to tackle this problem? You are definitely going to like encounter this sort of problems in your programs. Okay, so yeah, 0-1 knapsack, like you guys might have thought like the fractional knapsack is the complicated one and the 0-1 is kind of a like straightforward. Actually, 0-1 is the complex one. Okay, so that means if we have to take the entire thing itself, yeah, that involves a huge number of um, computation. So we have to resolve into dynamic programming in order to solve that. Okay, right. Let's look into the fractional knapsack where we can take a piece of a certain item where proportion where if we said this is worth 150 and we would take 1/10 of the item, it would still worth 15 something, right? Yeah. Also, just know that PE stands for pounds. Yeah, this is kind of I am using a different like modern made presentation elements. So yeah, this mistake that was made there. Right. So how are we going to tackle this? The idea is here we would call this the value. No, it's the value. Basically, it means it's the value of each item. So we are going to calculate the value of it, which means how much it is value. Suppose this is 5 pounds, right? Or we can say 5 kilos. So how much 1 kilo of this type D is worth? So we can say 30 rupees, $30, 30 something, right? It's the value. So in the case of A, we can see 1 pound is worth 200, right? Yeah, we are trying to guess which is worth the most when given this like or unit weight, right? We are calculating the V order. When we do that to all those elements, we get this. A that we order A is 200, B is 70, D is 70, B is 80, C is 70, and D is 30. Right? Okay. So suppose our bag can only carry 5 pounds, 5 pounds of items. So we have to take 5 units of these until like and get the most out of them. So if you take the entire D, you would get only 150. But if you take this single pound of A, you would just get 200, and there would be space for 4 more pounds, right? Yes. So here's what we are going to do. We calculate V or W, then like sort it in the ascending order. Sorry, descending order. The largest one comes first, right? Here it is. That's the case, right? A is the largest, B is the smallest. Now we would take most valuable item. Valuable by mean the density of values. Okay, so 1 unit of A is the most valuable. So we would take A and put it in a bag until either A becomes unavailable or a bag gets filled. So we have only 1 unit. So we can fit A here, and it's worth already 200. Then we can take B, right? We have 4 slots left. So we can take all 3 slots and fill our bag of B, right? Now those 3 slots are worth 240. Now there's only 1 slot left, right? We can take 1 from C, that is 70, right? Now the bag is filled, and these things are left there. However, when we do that, we get the most value. That is the way we can get the most. So, which is 510 according to this case. Okay. So how did that greedy idea came here? So we did calculate our possible scenarios, right? Then we knew that we only have space for 5. Now we would sort it and take the most valued position first, which is the uh, optimal solution at that point. No, if you would take this and run, we would get 200 immediately. So that is the local optimal solution. So we took that, then the next most optimal one, then the next most optimal. So we are like leaving this away, but we are getting the most out of it. So there are certain questions like you would understand it when you see one. Like we would have to resolve into greeting, right? Another one is like this. Okay, suppose we have like we know our computer, right? We can only process one thing at a time, and we have X amount of activities. Like we have this A1, which takes 3 time slots, and there's this activity A2, which takes 2 slots. Okay, like it takes 2 amount of time, like 2 uh, measures of time to finish. But here we have the starting time and the finish time, so we can calculate the duration. No? So there's this sort of things or work we need to do, and our idea is suppose we have only 14 seconds. We have to do most work in this time provided. So how are we going to do that? Yeah, that's another idea of tree. So we can just choose certain items, like if you take A3, it would take 7 slots of time, right? We can't do any work until this one is finished. So then we can maybe choose this one or this one. Since it finishes here, something has to start after this one. So either this, or this. Suppose they took this one, so it can use this one at the very end. So only 3 activities were done at that situation. Okay. So in this situation, you can see there are 1, 2, 3, and 4 activities. We can, if you choose those activities together, right? So there are so many ways to get those things, right? So how are we going to make a decision in an algorithm? So that's the greedy strategy. So there are 2 strategies, or there's this extra strategy. One is the early start time. So which starts first will be selected first. So basically, that would be this is the one that starts the very first. So we take this one and next one and the next one where there are no overlaps. So yeah, and another idea is this duration, which takes the smallest time, finishes fast, right? So we can just select those smallest ones and see what we end up with. It's the list duration. So the most efficient one, I think, is the number of overlaps. Okay. So we have all those activities, and we can see how many activities this one gets overlapped with. Because if we have an overlap with something else, we can't like perform all those. Like if we are performing this one, we can't do this one, this one, this one, or this one, because that would uh, like overlap the time, right? Yeah, if we are choosing this, we know definitely we are not going to do these things. We can't do that, right? So that way we can just say A has 4 overlaps, A1 has 4 overlaps. This guy has 1, 2, 3, and 4. This guy also has 4. So likewise, we can just calculate how many overlaps they have and take the least ones, the ones with least overlaps. So that might, yeah, the idea of greed is that might result in the least, like the most activities done, right? Yeah. So that is the concept of greedy. So there are so many other examples. I think that is the main concept of grid. So let's move into a different, like a different idea, which uses greedy algorithms in order to achieve this result, like achieve a certain outcome. Okay, which are called graphs. Okay, graph algorithms. All right. Right. Before I started, yeah, I promised that this is it. I would answer this question. Right. Yes. If you are calculating NPR and NCR, yes. In your case, yes, if we are considering NPR or NCR, the what do you call it? Let's say we are doing n minus r over n factorial into r factorial. It's one of those, right? Yeah, I don't yeah, actually remember, but right. Yes. If you calculate this by hand, the answers would be really small because this guy might result in a large value. This guy and this guy will also create large value. But when we divide it by those two, the resulting value would be really small. That's correct. But these values itself are large and they require a certain amount of computing. But if you are doing this by hand, we would just look into those values and we would just cross some time. That's how we calculate that by hand. But in computing, that's not the case. They would individually calculate those things. So basically, they are really large values, but the ending result is small. So that way, we need it's better if we can have a sort of dynamic programming, such as a lookup table or something, where uh, each of those factorial values are stored. So they can just retrieve it and use it, because in computation theory, this is completely out of scope, I think, but yeah, the multiplication task is the most time consuming or resource or computationally expensive task in our calculations. So adding two numbers really is easy. Subtracting, dividing, but multiplication, that's really hard for computers to do. So whenever those like, like such situation is occurred, it's we would use something like dynamic programming rather than resolving it into uh, computing one and other by itself, because that can affect our runtimes. Okay, so basically, what is a graph? And also, I should note that most of those materials are from some online uh, freely available resources. So the idea is, so you can basically search it, Google it, and learn other ideas, because if we are thinking about Geek of Geeks, GFG, Geeks from Geeks, yeah, they would have the same way of teaching, right? So if I would explain one thing, you might be able to understand the rest by just briefly referring. Okay, what is a graph? Graph is something like this. Okay, there are connections. So we would call uh, these lines edges and these nodes vertices. Okay. Yeah, that's just a mathematical way of explaining. Yeah, lines are edges, nodes are like those points are vertices. Okay, so there are two types of graphs. That one is directed graph and the other one is undirected graph. So think of this as a one-way street or two-way street. Okay, so directed graph means whatever it is can move from one place to other by following the arrowhead. So we can follow 1 to 2, but we can't follow from 2 to 1. Yeah, that's the idea of directed graphs and undirected graphs. We can move in either way. Yeah. So why do we need graphs? Suppose this is Google Maps. Okay. Yeah. This basically yeah. Keep in mind whatever I am teaching you is a basis for the very modern algorithm. So yeah, you guys should follow up on this A-star algorithm, which is used in Google Maps to like trace out our shortest path from one place to other. Yeah, but here we will be talking about Dijkstra, which was the simplest way, and the A-star is kind of a improved version of Dijkstra. Okay, so that's why we are talking about a star here. So right, okay, graph is like suppose think of those as roads. Okay, this is this may be our university. This may be the Gala Junction. This is the Peradeniya Junction. Whatever. So if we are going to like move from one place to the next one, or do something where we can we are finding how are we going to do that using the smallest steps or the smallest computation necessary. So that's where graphs come in. Okay. We have all those connections. So the things that appear on the edges, just on the lines, we call those weights. Okay. So by weight, that means, let's say from if we are moving from 0 to 1, it could take 4 minutes, maybe 4 units of something. So if we are going from 1 to 2, it would take 8 units, like that. Okay. Right. Right. So there are like, if we have a graph, there are two ways to search through a graph. One is called the breadth first search. The other one is called the depth first search, DFS. Okay. By breadth first search, what it will do is take a graph or a tree that have like basically works for the both ways. So take a graph, like select a vertex and search using the nearest ones. Okay. So breadth means suppose I can explain this easily using a tree. Like trees also a graph which doesn't have this like these four are connected all together, right? But in a tree, there are no like these cycles. That's the only difference in uh, okay. Either way, let's go on. Okay, suppose we have a tree, and we have like search for an element in a tree. Okay. So the thing about trees is, and also graphs, you can start from one point and you have to move over and over until you find it. And it is kind of a very challenging situation where it's like going through a maze, right? So how are we going to search for something? So breadth first search means we would start at the point. Okay, suppose this one is our point. Okay, so we would then select the ones that are very that are adjacent to it. Okay, this one is adjacent, this one, and this one. And we would search going through those things. Okay, suppose we would choose 0 and the adjacent ones are 1 and 2. We would look into those two and see if the number or the value we are looking for is there. If it is not, then we would anchor in these two places and we would just look at the ones adjacent to those ones. So here it would be these leaves. In this case, 3 is adjacent to 1, 2 is 4 is adjacent. So in the next iteration, they would look into those ones. So that's basically what BFS means. All right. Let's just quickly look in. Like, yeah, we chose the 0th one, and I should mention that in BFS search, a queue is used to like keep track of what are the points that we are traversing. Okay. We would just put the 0 into queue, and yeah, and we would take the nodes that I just. If that's not there, we would just suppose we look into 0, right? We visited 0 and it's not there, so we would just put 1 and 2 into the queue. And then since we have selected the 0th and it's not there, we would just remove it from the queue. So we have 1 and 2. So we would search 1. Yeah, it's not the value we need. So we would take 3 and put it in the queue. Afterwards, if that's not there, we can just remove the 1. So in the queue, we have 2 and 3. Afterwards, we do the same thing. Okay. Take 2, search. Yeah, it's not there. So we take the adjacent one, 4, and put it at the end of the queue. So the next element we would be searching is 3. Why? Because we searched 1 first and the second one second. So the next one is going to be 3. And then comes the 4. So yeah, basically a queue key helps us to keep the track of each and every element, go iteratively one by one. That's one way to search through graph for a tree. So the second one is DFS, which stands for depth first search, which as it means, it would just take a node and select a node, go there, select a node from there, and go there, and select a node from there, and go there until there are no more ways to go. Once that happens, it would just come back, and if there's a node here, it would come back here, and then move to this place. Yeah, that is how DFS works. Yeah, let's see. So we selected 1, 0. So here we are using a stack. Okay, right, and right, we have 3 adjacent nodes, 1, 2, and 3. So we will put that in the stack. And right, let's move into direction. We went there, visited, and yeah, that's the one we are looking at. So we come back and go in another direction. So we took 2, and yeah, so we have 3 and 4. We can trace. So since 3 is already here, we would put 4 and move there. So since we have like visited the whole path, so we can come back and go to 3. So that way, the entire graph is traversed, like all the nodes are visited, and something is like we can search for something. Yeah. So these two ideas, like BFS and DFS, they become like really efficient in different cases. But DFS basically goes down in one direction, and if the value we are looking for is not found there, then it comes back and then goes again, tries again. Okay. BFS, it could just search layer by layer. So if I am going to give an example, a pathfinding algorithm most likely would provide BFS, breadth-first search, because if there are many ways that we can go, it is a kind of a good idea to go with, like, move on every direction until one would hit the target. Otherwise, the other idea is go in one path until you're stuck or you reach the destination. If you are stuck, come back and turn from some other place and repeat. Yeah. So Dijkstra's algorithm is like we know, like we have a starting place and we have a place where we want. Okay, like just like navigation or Google. So we are here. We need to go here, and yeah, we are using this on weighted graphs. Weighted means it would cost some amount to cross a certain place. Okay, if we are moving from 0 to 1, it would cost 4 of something. Maybe 4 seconds, maybe 4 units of computation, maybe something. Okay, it would cost this amount. So the Dijkstra algorithm basically calculates the most likely the easiest or the shortest path from one place to the next. Suppose I'm going from 0. So there are many ways we can go, right? We can go like this, or we can go like this, or we can go crazy and go with something like this. We have so many ways we can achieve that result, right? Okay, so what are we going to do? We have to decide on a starting node. Suppose let's say we are starting from 0 and we are going. Okay. So how are we going to do this? We are going to select the edge least weight, which is 4 in our case. So we would just say we can go there. Then we have like we have these two nodes selected and we have 3 edges connected to them, right? We have 3 paths we can follow. Then we are going to select the smallest value. We can either select this 8 or this 8, right? Select one and do the same thing again. If you select this one, we have 2, 7, 11, and 8. So the smallest one is 2. You go here. So we can do this until no cycles are made. Okay, so we can't just do something like this and create a closed circuit, closed loop, right? If you do that, this should like make a closed circuit, closed loop. So we have to do this again and again until all the nodes are reached, but there are no cycles made. Okay, so we chose the 0th one, and we can go to the first element with only cost of 4. Okay, then we have 2 choices, right? Either we can go from here or here. So yeah, they would choose here we has chosen this path. So it would cost 8. To go here, it would cost 4. So to go here from here, it would cost 4, then 8. So that is 12. Here, 8, then 7 to here. So which is 15, then 1 to here, which is 9. Okay. So in the next element, they would just look at these 3 points and select the smallest, which is 9, and go there and do the same thing again and again until the whole graph is covered and we reach the destination. Yeah, that's the Dijkstra algorithm, which sounds simple, but it's of different to implement. But yeah, that's the Dijkstra algorithm, right? So the final video for session, hashing. What is hashing? Hashing is basically an idea we are using with all other like DSA methods. So we can do quick searches. Okay, an idea of hashing is find something very quickly. So we are, suppose we have a set of numbers or locations or something. We are going to store those things in such a way that we can just immediately retrieve one value without doing much calculation. Okay. So if we have an array and we have some numbers in it, we have to search one by one or something to find a value. No. So other than doing that, if we can immediately know where the value is stored, yeah, that's what we call hash. So we call the searching idea lookups. Right. Let's see. So we have the set of values and we have this function called hash function. So yeah, we make a table which is an array most of the time, where the index is, we call the key. Okay, suppose we have these numbers 10, 12, 5, 6, and 9. Okay, we have those numbers, and I think you guys know the modulo operation, right? This symbol law mod, which means if you divide a value from some value, what is the remainder? Okay, let's say our hash function is modulo 10 or mod 10, which means if you divide the value by 10, what is the remaining? Like if you divide 10 by 10, remainder would be 0. Right? 12 by 10, it would be 2. 5 by 10, result will be 0 and 5 remain. So the remainder is 5. Likewise, so suppose our hash function is 10, mod 10. So we can map each of these, like if you would each of these values into the hash function, we have 0, 2, 5, 6, and 9, right? So let's say we have an array. This is the very primitive idea of hash functions. Okay, so we would store 10 at the index of 0. So 0th index we store 10. In the index 2 we store 12. In the 5th one we store 5. And the 9th index we store 9. And likewise. Okay, so say we need to find 5. Okay, so do we have to go one by one here? No. We would just put the value into hash function. Hash function returns 5. So definitely value should be there. So if you go to the index 5, it will be there. If that value exists, it will be there. So we don't have to search. Basically look up. That's the idea of hashes. So think of a situation like this. Okay. I would say 10 and 20, and now hash function is modulo 10. What would be the resulting values? 10 results 0, 20 also results 0, right? Okay, we would store 10 here, and when we are trying to store 20, we are going to have 5. The value is here. There is a value already there. So we call this collision. So most probably we are going to make hash functions in such a way there are no collisions there. Okay, we would make it in a way there would be no collisions. If there are collisions, there are two ways we can handle this. One is called the linear probing. This one, next one is called separate probing. So we don't just have like dive into that. I would just tell you the idea, gist of that. So if there is a collision, one way is, yeah, we would the zeroth index. Yeah, there is a value. So you would store it the next value in the adjacent slot. You just store it in the 20. Okay, so when you're searching, then suppose we have to look for 20. It would put it in the hash function and it would return 0, right? Then we would come with the 0th index and check. Yeah, that's not the value. So we can just look at the next value itself and see whether that is the value. Okay? Because we know that when we are storing, if there is a collision, then we are storing it in the next adjacent. So if there is a collision there also, we would assign it in the next one. Likewise. So yeah, that's a really cheap way of doing that. Yeah, that's one way of doing that. Other one is make this each value into an array or a list, most likely a linked list. So if there are two values or collision, first value will be in the first element, second one will be next one. So basically 10 and 20 stays in the same bucket, if you say. But there will be another array inside. Yeah, that's the gist of that. Okay, I think yeah. So you guys might be wondering why the hell I'm teaching you guys, sharing it with you guys these different ideas. All right, so I can suggest you like the lead code might be the go-to site lead code and the code process, both of them. Yeah, lead code might be the one that you might know uh, right after hacker rank, most likely because this is kind of a new, like a modern interface than the code forces. So yeah, I was code force it run like in 2020 or something, but is it I'll answer the questions, please. Give me a second. Okay, so yes, I am just like I have handpicked a couple of questions that you guys can basically go there and try. So one is question number 1091, which is like I'm just giving you hints all over, but try it yourself. Yeah, this one you have to use BFS. Okay, first search because this is pathfinding one. So you will have like just BFS. You can find the answer for this very easily by using BFS. You can use Python if you are comfortable with that, or C++, C, PHP, whatever. Okay. This one you can use solve it by BFS. I'm just naming questions because you guys know the idea, so you can apply it and see how the theory differs from the practicals. Okay. So the next one is number 200, which is also a pathfinding-ish thing, which looks into the connection of those islands thing. Like they are looking for the longest path. So you will have to use the depth first search here, DFS. And in network delay time, here you will have to use Dijkstra. This is an example of having to use Dijkstra. And this T15 one, yeah, you can see the size of the array is really huge. So the ideal solution for this will include a merge sort. And in 920, 912, you can do this like the most optimal way of